All right, let's grind out some more of these results section. This is a slow, arduous, but ultimately very worthwhile process. Let me shift over to my other screen here and pick up where we left off. Hopefully you can see this page now. 3.1.2, changes in phase diagrams with the homology of the acyl part, Cy, y equals 1 to 4 of ethyl carboxylates, Cx plus C2. Wait. All right, where'd my y go? All right, so let's go back. So last time it was CX. So let's see. So double bond O, O, and then you've got a C and a C, and this could be X or Y, and this could be X or Y. So alkyl acetates was last time, and well, we do have the whole World Wide Web here. So let's share screen and let's just make sure we know what we're talking about. So hexyl acetate, smell, nice. Let's go for structure. Okay, so hexyl acetate has, right, has CH3 and C6H13. So hexyl acetate. So acetate, acetic acid. Acetic acid has two carbons, and actually that looks just like acetic acid with a hexyl group attached to the O, which I'm sure I should have known. And so the X, C double bond O, O, CX, CY, I'm guessing. And okay, so hold on. So stop share. And so hopefully now you can see the page here and what we've got, drawings, extreme zoom. So we said hexyl acetate had the 6 carbons here. So that means X in this place right here, X equals 1 to 6 is X. I think this is going to be Y. So, all right, but let's go back. Stay on there. Oh, there we go. All right, so now into back where we were. And there we go. All right, so we were down here. Y equals 1 to 4 with ethyl carboxylates. So I think, let's see what happens. But this is going to be C double bond O, O, C2. That's going to be the ethyl part. And we're going to have CY over here with 1 to 4 carbons. And the 2-1 we've already done because the 1 we've already done because there was 1 carbon here in addition to, all right, so then the next question becomes how do they count these? Let's see. ETAs, ethyl acetates, would be 2 carbons. Ethyl carboxylates, right? So 2 carbons there. Oh, all right, I think we're getting closer anyway. So Let's see. Good. All right. So now let's read on. Figure 3AB show comparatively the Windsor 2 and Windsor 4 curves, respectively, for 4 ternary systems employing different ethyl carboxylate homologs, while Table 2 summarizes the percent areas of the domains delimited by these curves in the phase diagrams. From the data, it can easily be seen that although the Windsor 2 domain for the ternary system with ethyl acetate is the largest, both the Windsor 2 and Windsor 4 curves are uplifted in comparison with those of ethyl FO and ethyl, propyl FO form O. So FO form oxalates, I'm guessing, for 1 carbon. Therefore, surfactant demand is higher, period. Ethyl butyl has both the narrowest Windsor 2 area and the highest surfactant consumptions for achieving either Windsor 2 or Windsor or 4 phases. Similar to its metamer methyl acetate, ethyl formate did not allow the formation of Windsor 2 phases at high water-oil ratios, figure 3A, bottom right corner. Its volatility is inconveniently high, and the Windsor 2 domain is the smallest. Thus, the metamer of propyl acetate, ethyl propoxylate, is most convenient for Windsor 2 extractions in this homologous series. Now, what I really like about this paper is that it's so systematic. It's trying all the different ones for both sides. So it's changing the carbons on the X side, it's changing the carbons on the Y side in a way that's, again, is something we can potentially do over time. And these are encouraging things to see, encouraging analyses. All right, we've got the tables here. Let's go over and look at them for a minute. Where's the paper? There it is. And share. All right, this is methyl acetate. And now I know that it always shows this when I share. So I'm not sure I had to change volume there, but all right. So we just read that. Ethyl formate. Right, it really propionates. Ethyl propionates is the green. It goes all the way to this corner almost. Goes very close to this corner here for the Windsor 4. But again, so we do have not, okay, when they're miscible, they're not microemulsions. And we have these nice sort of rounded regions, or they're not so nice. I mean, they're not very rounded except for the green one here. But yeah, okay, so they have said that they like the ethyl propionates and the propyl acetates. Propyl acetate is pink here, has a decent region, goes all the way to the corner. So anyway, interesting, very interesting. All right, also let's stop sharing. Let's go back to here and keep reading. Did we finish? Yes, we did finish that. Keep going. All right. Here's the relative areas. Ethyl formate, acetate, propionate, butyrate. Yep. All right, so it likes this one. I mean, okay, yeah, no, I'm not convinced that, I mean, I guess it is the best of the worst. It's, All right, but keep reading. Based on the results above, all further work on establishing and characterizing phase transitions in these microemulsion systems was focused exclusively on PRAC and EPR, propyl acetate, and ethyl propionate as oil components. Ternary microemulsion forming systems based on water, bridge 30, and ethyl acetate have been prepared before and are described in the literature. Yeah, I'll say. So, Mihaly et al. Were the first to publish the phase diagram of this system at 25 degrees. Our phase diagram is nearly identical to theirs within experimental errors. Good. Flanchu et al. Went further and studied how the phase diagram changes with changes in temperature and noted that only at temperatures below 15 degrees Celsius are Windsor 1 phases observed, while temperatures higher than 40 degrees Celsius caused an enlargement of Windsor 2 phase domains. This explains why we did not observe any Windsor 1 domains, as our working temperature exceeded the phase inversion temperature of 15 degrees Celsius. Good. Phase inversion. Good. So phase inversion temperature seems, so Windsor is like a Windsor 1 to Windsor 2, and Windsor 1 to Windsor 2. Okay, mental notes. Temperature can affect that. I still don't understand it. So keep going. Similarly, the system with butyl acetate as an oil component has also been reported several times, although always as an extraction system for either metallic ions or dyes from contaminated water. So these guys are doing something similar to things that have been done before. There's no complete phase diagram available in the literature for this ternary system. Kadar et al. Reported a pseudo-ternary phase diagram where acetone was added to water as a fourth component, and the aqueous phase was in fact a solution of cobalt tetrabiocyanoate-ish ions. While their Windsor 2 curve is very close to ours, the Windsor 4 curve is much lower, likely because acetone increases the miscibility of the phases. So that's a key word there. Likely means we can make arguments, but notice there's no other things here. Ethyl butyrate has also been reported as the oil component of some microemulsions for various drug delivery systems. Interesting. Drug delivery. Albeit with other non-ionic surfactants such as bridge 97 and tween 80, or polyethylene 10-dodecyl ether. So interesting, tween 80 and pi. So drug delivery, that's a star. Other surfactants, that's a star. That's things I want to find at some point. And well, there we go. I think we're done there. And I don't know how far we're going to go on because effective co-surfactant, salinity, and pH, maybe effective addition of different amounts of isopropanol as a co-surfactant. Just scanning this over. I mean, maybe we've done enough for now. And maybe we can take a break while we're here. Let's just flip through. Densities, refractive indices. Anyway, we'll have to decide what other parts of this we want to read. In a perfect world, of course, we read it all. But well, let's see. So the next part of this is going to be presenting this work to a group meeting. And so we want to be able to think about if we have enough to do that, or we'll think about it, and we'll either see you we'll see you